While we're just getting set up with the screen share, welcome everybody to today's session. I know there's a lot to coordinate right now with the new world we live in, and you guys focused on doing pretty much all your teaching virtually. So hopefully you'll get some good ideas out of today's webinar. So what I'm going to do is I'm going to step through a couple different data sets, so a couple different problems that aren't your typical easy, classroom textbook problems, and then show you how JMP has some tools that sort of can analyze these little more complicated situations quite easily. The first one I'm going to start off with is just going to be visualizing data. So I'm going to open up this data set here. Now, each data set I'm going to open, I'm just going to give just a high-level description of what it is without getting into too much details. But basically, this is data that was collected by an entomologist studying the population of a particular insect across these different test regions. And I'm going to show you what that is in a second here. In fact, I'll just open up this map I already had built. So this here is a map. This happens to be Alberta, Canada. I'm kind of zoomed in, so it might be hard to discern that, but this is Alberta, Canada. Each one of these red dots is one of the sites where they're measuring the density, the population of this particular insect. So I'm going to close this up. And actually, let me just sort of summarize this data through a distribution so you can kind of see what we have going on here. I'm just going to basically, I just want to show you some histograms. So this is just illustrating that there are 74 different sites. So that map I showed you, there's 74 different locations that they're measuring. You can see the names of them. But the reason why I'm looking at this is just to illustrate that we don't have data evenly collected across all of the sites. And so you can kind of see here, like this first one, we've got 36 years worth of data, this next one 33, but there's some that you can see. Here's one that only has 2, there's another one that's 2 and 13 and 9, and so on. In fact, that's sort of illustrated on this next little bar chart and table here, showing the amount of data we've got collected starting from 1970 all the way to 2016. So you can see that the earlier years, we don't have as much data collected as we do during the latter years. So that's all about, which sites started getting measured. Okay, so let's talk about, well, how do we want to look at this? So since this is data collected over time, let's look at it in a sort of a time series view. So I'm going to grab density, I'm going to put it here, I'm going to grab year. Now this has got all the locations, so that's why it's looking a little messy at the moment. So I'm going to just bring up this data filter so I can filter by location. And so this is what's going to allow me, click on the connect lines. So this is what's going to allow me to look at, okay, here's a time series graph of this first site, Acadia Valley, right? And we've got 36 years that we've collected data on them. And so the more grasshoppers, the higher the density, and so you can kind of see the height of that. And I can, over here with this data filter, just click on each one, and now here's what gets tricky. I get to some of these locations that, here's one, Big Lakes, that only has 11 years that it was, data was collected. Here's a couple that only have 2, and so on. And so remember, there are 74 different locations. So clicking through here to try to look for patterns is a little cumbersome. Okay, there's a lot to compare, and especially, I think the real thing that's making this challenging is we don't have data collected every year. So as we go through different graphs, like here's one right here, it's got 2 years, so you're only going to see 2 points. So it's kind of hard to sort of look at this. Well, there was actually one that only had 1 year. So let me show you a really cool way that JMP allows you to look at this data through it and through an animation. So what I'm going to do is I'm going to bring up a tool called the bubble plot. And I have latitude and longitude, so I'm going to put those in there. Location is the ID, year is the time. And what I'm going to do is the size of the bubble is going to be the density, the amount of grasshoppers in these sites. So I'm going to click OK. And what I'm going to do is, to make this a little easier, I'm actually going to put on the map. Okay, I'm going to make this a little bit bigger here. Okay, I'm going to just zoom this kind of around so you can zoom in. Okay, so this is year one, 1970. Okay, and remember, we don't have all of the sites measured every year, so we can just see the set that's measured on 1970, and the size of the bubble is the density, the population of that insect. Now, I have data collected from 1970 all the way to 2016. So what I'm going to do is I'm just going to hit this play button. And what you're going to see is, as I index through the years, I'm going to see kind of two things going on. One is I'm going to see new sites that get added. So you'll, right there, right? We just saw a bunch of new sites get added. And then the population is shown by the bubble size. And so now we can kind of, through this animation, visualize when there's big blooms in the population. I think there's one coming up right here in the early 2000s. Boom, right there. You see these big blooms of the populations, and then they start going down together. We can also see how maybe different regions, like those in the Northwest or those in the Southeast, might be changing in different patterns. And you can see that this is a lot easier to view. I can also stop this and just sort of manually, I can manually move this around if I want to hone in on particular time periods. And from this, I can kind of study it, I think, a lot better than trying to look at the time series graph. So this is that period where there's a big bloom right there. I can kind of move around and study it. So this is a very, very simple way to create this bubble plot using size of the bubble. And then I've got location, dropping a map on it, and then I can watch the changes through an animation versus, I'm going to close this and just bring up that time series graph we had. That's, I think, a lot easier than moving through a time series graph and trying to find patterns, right? That's really, really hard to do that. So it's a very, very simple way. In fact, I did a second graph, but instead I added another dimension. So the size of the bubble here is the density, the population, and I set up a color variable so that when it's green, and I've got the information over here, when it's green, it's showing you the percent increase from the previous year, positive, and when it's red, it's showing you that there was a decrease from the population of the previous year. And then the gray I kind of have in the middle, this minus 25% to plus 25%. So now I can do the same sort of thing, click through in the year, and now I've got two dimensions going on, population size and percent change from the previous year. And so now this isn't, I guess I'm sort of doing an animation by clicking through, but it's not the same as the bubble plot. So you can see, I'm going to click on, see 2003, almost all of them had an increase in the population size. There were some that didn't. And then I go to 2004, and there's a decrease. And we kind of saw that through the movement of the bubble plot, but this is bringing in another dimension. So I think these two views, this idea of dropping these bubbles, these dots with different sizes and different colors on a map and letting that animate or manually moving through, I think it's a lot easier to see sort of those patterns than trying to look at, I mean, there's 74 different time series graphs. That's quite challenging. Okay, so that was the first one I started off with. I just wanted to do something really, really basic. Showing something in a graph, but let's move on to something a little bit more statistical in nature. Okay, so this data set here is data that was collected on a marketing advertising experiment. And so what was done here is there's 10 different time periods, and these happen to be weeks, right? So we got week 1, week 2, week 3, week 4, and so on, all the way to week 10. And during each of those time periods, a website was placed with a different advertisement and promotion. So we've got 4 different ad styles. We'll just call them 1, 2, 3, and 4. And for each ad style, we can offer different promotions, right? Different, maybe a percent increase, decrease in savings, or money off, or a coupon, right? So there's different promotions and advertisements. So there's a total of 12 of them. So I'm just created this other column. So you've got the 12 different combinations. And then the response variable is, this just stands for website 1, okay? And the data is standardized, so just positive number means something positive, and negative it's lower than average. But that's not important that we know the exact value. Just get that the higher the number, the more, whether it's click-through rates or conversions or views or whatever it is. Okay, so I'm going to just make a graph of this data. Okay, bring up JMP's graph builder. I'm going to put in the response variable there. I'm going to put in 3 different promotions. There's 4 different advertisement styles. I think actually I'm going to make promotions color. I'm going to choose to display not only the data, but the mean and a confidence interval for the mean. And so this is sort of a way to do the comparison. And I can do other views if I want it all together. You know, I could do it like that. And so I see all 12 going across. In fact, maybe, actually, let me do it like that. That might be easier to see what's going on. In fact, and also I'm going to change which one I use for color. Okay. And then, in fact, I can even add information for hypothesis test, you know, Oneway ANOVA to see if there's differences there. So right up here in the top, you see how I've got the F statistic and the p-value. Now, it turns out that they just didn't run this marketing campaign on one website. Turns out they ran it on 125 different websites. Okay, I have those variables hidden, but I'm just going to drop it down over here. So you can see we've got 125 different websites. Well, inside of the graph builder, it's actually really easy to do this because I can just choose to swap out. And I'm pulling up this tool in JMP called the column switcher. And what this allows me to do is over here on the left, I can just swap through whatever variable, in this case, whatever website I want to look at, and I can see those 12 combinations of advertisements and promotions, and I've got the test statistic up there for a test of if there are differences in the means. And as I click through, you can see certain cases, like here's website 12, where advertisement 1 across all 3 promotions did much better than the others. So I can kind of click through here and see where some of those differences are, things where there's not many differences. Oh, here's one right here where promo 2 across all the 4 advertisements did much lower than the other 2 promotions, 1 and 3. But again, this is kind of cumbersome. I've got 125 of these to click through, but still very useful to do it like this. So I can also, I'm going to bring up JMP's tool, this Fit Y by X platform. This is what's going to allow me to get the display for a Oneway ANOVA. So I'm going to do this here. So I've got a graph at the top. So this is similar to what I did in the graph builder, except now I'm getting much more information, the results you would see in a one-way analysis of variance. In fact, I can even do multiple comparisons. Oh, scroll this over so you can see it. So in addition to the results of a one-way ANOVA, I've also got down here every possible pairwise comparison shown, right? So quite a bit of output. And just like I did in the graph builder, I can bring up this column switcher. And what this allows me to do is same thing I did in the graph builder. Over here on the left, I've got this column switcher. And then now I can just swap through which response variable is being used in this one-way analysis of variance, right? And as I'm clicking through, you can see all the output, see how all that's changing. But again, this is kind of cumbersome to go through 125 of these, looking for the ones that are significant and the ones that are not. So, well, guess what? JMP has a tool to do that. So I'm going to launch this tool in our screening platform. It's called Response Screener. Okay. And what I'm going to do is I'm going to put 125 responses up here as the Y, and I've got 1X, this add promo. These 12 combinations of advertisement and promotions. I'm going to hit OK. And so what JMP just did very, very quickly is it ran 125 analysis of variances for me, brought up this data table, and each one of these rows is one of the responses. So here's website 1, website 2, website 3, and so on, all the way to website 125. And then going across are all the sort of common metrics we might look at in an analysis of variance. Okay, we got things like summary statistics like the mean. We've also got sums of squares, the mean squares, the F statistic, the p-value, R squared, the effect size. You can sort of see all of that. In fact, what I'm actually going to do is, I'm just going to sort this. I'm going to sort this table here. Wait, hold on here. Oh, I think I might have something. Oh, I got to close this. All right, let me do this again. Okay, so I just sorted it by the p-value. Okay, so basically the most significant ones are on the top, and as I scroll down, they're becoming least significant. And then JMP identifies them here in red, so you can kind of see right here, there's 36 different websites where there was a statistically significant result across these 12 combinations. And I can look at graphs for that. So over here, JMP automatically creates a set of graphs. And so I'm going to click on this one first here. Now, what this is a plot of the p-values. Okay, so you get a plot of all the p-values. Now, there's two here because there's sort of two ways to think about this. One is I can plot the actual p-value, which are the red dots, and then I've got to adjust the cutoff because, well, it's this concept of multiple comparisons, right? I've got 125 different tests going on here. So it's sort of adjusting what is the cutoff based upon that. So you can see that the red line isn't even, or I can fix that at 0.05, say that significance level of 0.05, that's the blue line, and then adjust these p-values for that concept of multiple comparison. Either way is the same thing. In fact, I'm going to just zoom in here. I know that's kind of tiny, so I'm just going to show you so you can see it a little bit closer. And so the exact point when the red dot, the p-value, crosses the adjusted significance level is the same point when this adjusted p-value is going to cross the 0.05 significance level. Let me zoom back out. Okay, so this is a way that I can easily identify through this graph those ones that are statistically significant, and I'm just highlighting them there in the graph. And if I go back, I've already sorted it, so it's not necessary that I do that, but you can just see those are those same ones. And there's some other graphs too, like I can do a plot of sort of that concept of log worth, which is basically just a function of the p-value. It's sort of based on a log scale because p-values are hard to compare unless you log it. So the same thing. Now I've got on the x-axis the effect size. So, you know, I can sort of see the ones that are significant have a large effect. And then when that log worth is telling me it's significant. And then there's already a script written to fit Oneway ANOVAs for those ones. So if I highlight these ones that are significant and click on the script fit selected items, now, actually, let me add the output here. So you can see it means ANOVA, and I'll even add the multiple comparison as well. Okay. So there's a lot of output here, but basically I have 36 different Oneway ANOVAs. So here's the first one, which is website 55, the most significant. That's where the biggest differences are. And I've got all the standard ANOVA output, including multiple comparisons. So look down here. This is a big table of all the multiple comparisons. Then the next one, website 39. That's the second most significant one. And again, all the standard ANOVA output, multiple comparisons so I can look at. So what JMP just did is it allowed me to do, and I'm just going to close these up just so you can kind of see this list that we've got here, and I can open up and close any one I want to see. So basically, I have the 36 Oneway ANOVAs that were the significant ones separated from the remaining ones that are not significant. So it's just a really quick way where I can do 125 one-way ANOVAs very quickly and have JMP summarize those results and identify the significant ones for me. Now, I did this in a one-way ANOVA context, but this could have been done in a regression context or maybe a two-sample t-test because I was able to sort of pull up this screening tool and look at many responses at once. And I think this kind of thing is good to think about now because I know traditionally in classroom environments, we sort of typically do smaller problems, right? We're going to just do one-way ANOVA or maybe two of them. But the reality is when you kind of get out there in the business environment now and your students get out there, this is a perfect example. They're not going to run this experiment on one or two websites. They're going to run this experiment across, in this case, 125 different websites. So I think it's actually a good idea to start exposing your students to some of these concepts. Now, I know this isn't a classic big data problem, but it's still a lot of data. And that's kind of what your students are going to see when they get out there. They're going to see scenarios where there's a lot of variables to study, not just one or two. And JMP has some tools that just make that really easy. And if your students can understand a one-way ANOVA, then I'm sure they can understand 125 of them at the same time, and then just ranked and sorted according to the ones that are most significant to the least significant. And now we know the websites, in this case, to focus on the ones where there were effects between advertisement and promotions. And then we can just easily drill down. So again, this makes it so much easier to look at a lot of variables simultaneously instead of trying to flip through 125 different one-way ANOVAs and find the ones that are significant. JMP will just do that very quickly, automatically. Okay, so that was the second tool I wanted to show you. The third one is I'm going to show you this tool called Predictor Screening. Okay, so what is this problem? This is a printing example. And so this is, think of, printing on paper, right, in a commercial printing environment. Not your little printer at home, but in a commercial printing situation. So there's this response variable called banding, and banding is a undesirable effect that happens in printing. And so I've got this color coded. So those that have no banding, which is the desired result, I've got them coded green, and then the ones where there's banding, you can see I've got them coded red. Okay, now so there's only 17 observations here. Okay, so we only got data on 17 different sort of, these could be printing jobs. Now, I've collected data on a whole bunch of other variables. Here's one called grain screen, there's paper type, ink type, solvent type, et cetera. You see this going across, and we don't have to dig into what each one is. The key is that there are 26 of them, okay? So I've got 26 predictors. I've got them listed over here on the left if you can see them right there, or we can scroll through the worksheet. So there's 26 predictors, but there's only 17 observations. Okay, so we know that we're running into a little bit of a challenge right there. We've got more variables than we've got data points. So it becomes challenging to build sort of a model, whether it's an explanatory or predictive model, and it becomes hard in this case to often find the variables that are important because either a lot of them are going to be correlated with each other. With so little data, once one term maybe comes in the model, it might be impossible to find any others, and I'm going to illustrate that. So I'm going to use a technique, a modeling technique in JMP we call partition, and I'm going to put in the response variables banding, and then I've got all 26 predictors in here, and I'm going to hit OK. And so for those of you not familiar with partition, basically what's going to happen is, okay, so I've got 17 observations, and 9 of them have no banding, that's the positive result, and 8 of them have banding, which is the negative result. So what partition does, I'm going to hit the split button in a second. So what partition does is it's going to scan through each one of these variables. I'm going to move this aside so you can see what I'm talking about. Like it's going to switch, for example, between grain screen, yes and no, and then paper type, coded, uncoded. And then for continuous variables, you can think it's sort of scanning across. And what JMP is going to do is find the variable and the spot at which to cut off that variable such that it causes the biggest difference between the percentage of observations that have banding or no banding. Now I'm just going to do something here just so I can see some information as I do this. Okay, so remember, I've got 9 no banding, 8 banding. So I'm going to hit this split button. And so the variable that it found was viscosity. And so basically, there are 6 observations that have viscosity over 50 or 50 or more. And for all 6 of those, there was banding. And then over here, there are 11 observations that have a viscosity below 50. 9 of them have no banding, and 2 of them have banding. Okay, so that from scanning all of the variables, it found that created the biggest difference between the percentage of banding and no banding at that point, at 50. Okay, and it scanned every single variable, and that was the first one that could cause the best split. Now I can split again, so I'm going to hit the split button. So now what it did, let me scroll down so you can see the tree diagram. So of the 11 observations here that have viscosity below 50, and remember we had some had banding, some didn't, it took those and it split those again. And we now have a difference between grain screen, yes or no, and those that are experiencing banding and no banding. And so you can see that if viscosity is below 50 and there's no grain screened, then all of those had no banding. If the viscosity is below 50 and there is the grain screen, we have 3 no banding and 2 banding. Okay, or you can look up here in the diagram, right? So here is, remember here, there's the 11 observations that have viscosity below 50, and if the no grain screen, there's 6 of them, there's no banding. And then of the 5 that are below 50 and have grain screen, 2 have banding, 3 have no banding. Okay, so it's sort of, remember, it's scanning through all of these variables, finding where to split. And I can hit split again. I can keep on hitting split, and it's not splitting anymore. And what's sort of happening here is that there's so little data that it can't find a place to split these to find any more difference. And so at this point, I would be left with this idea that there was only 2 variables, viscosity and grain screen, that are important. But there's a challenge when you're dealing with situations like this where you have more variables than data. So JMP has another way to approach this. And so I'm going to open up that partition tool again. But instead of doing this decision tree, I'm going to do this thing called a Bootstrap Forest. And I'm going to hit OK. Now I have some options here of how many trees I want to build. I'm actually going to change that to 1,000. And what I'm going to do, in fact, I might even lower the number of observations that have to be inside of a tree. And I'm going to hit OK. Give it a second here to search through. I'm going to close up some of this output because I just want to focus on a specific set of output here. Okay. So what did JMP just do? Well, what JMP just did is it built 1,000 trees. And I can scroll down here. You can see there's 1,000 different trees. And I'm going to open up this first one just to show you. Okay. And this tree is small. It only has viscosity as splitting, and it doesn't split any more than that. And, okay, here's the second tree. This one has paper mill. It split first, then it followed by viscosity, and then it followed by this variable called unit number. Again, so here's another one, paper mill location, then this varnish percent. So each tree I open is different. So you're thinking, well, what's going on there? Well, what JMP is doing is it's randomly selecting a set of variables to use for each tree. Now, it also is doing a bootstrap the other way and doing a sampling with replacement. But let me just focus on the idea of sampling different variables. Why would you do that? Well, think about, in fact, actually, I'm gonna manually do that so you can get the idea. I'm gonna open up the partition again. Keep that over there. Let me just show you the output, if you remember. So remember, viscosity was the first split when we sort of built the partition tree manually. So it's split by viscosity at 50. So imagine I do this again. Now there's a lot of variables, so let me scroll this down so you can see them all. Let's say I build this tree again, but I take out viscosity. So in other words, I'm saying, okay, JMP, build a tree, but don't use viscosity, which I know when I thought of all the variables, it was the most important. But now I want to give the other variables a chance to weigh in here without sort of being influenced by, once viscosity explained everything, it didn't give those other variables a chance. And so, whoops, I got to do that again. Apologize, did that wrong. Partition, recall, make sure viscosity is out. Okay. Decision tree. Just make sure it's not there. Yep, okay. So here's the same setup, right? I've got 17 observations, 8 of them with no banding. So now if I hit split, the first variable it found with the biggest difference was paper mill, okay? So there are 5 observations where the paper is from the Canadian mill, and all 5 of them have no banding. Okay. There are, let me make sure I grab it here. Okay. There are 12 observations from the US paper mill, and 4 of them have no banding, and then 8 of them have banding. So if I take viscosity out of just the candidate set of variables it can split by, it's like, well, if that's not there, paper mill is actually important. Okay, and so I can build this tree and find out what's next. And it's like, oh, what's next is this variable called wax. So if I take the US paper mills, that's these right here, and I split it by this wax variable, for those that have a wax less than 3, there's 6 of them, they all have banding. For those from the US paper mill that have wax 3 or greater, okay, and there's 6 of them there, 4 have no banding, 2 have banding. Okay, so now these 2 variables that weren't in the first tree are now part of this partition I've done with viscosity not there. Okay, so think of this idea that I can manually go through these trees, build all these trees, but only let certain variables be candidate variables to even be considered. Okay, so that's basically what's going on. But to do that manually would be incredibly cumbersome. In fact, in this case, I did 1,000 of them. That would be, you know, you wouldn't do that at all. That would take an enormous amount of time. So JMP is sort of doing this automatically. It's randomly selecting a set of variables to be considered for the tree and building a tree. And so that's what each one of these trees are. Okay, I'm just kind of opening some of them so you can see a summary of what's being split. Now, why would I do that? Well, if I go through that process 1,000 times, there's going to be variables that have a chance to come into this partition tree because they are part of the candidate set, because I excluded a set of variables that could have been candidate sets. And if I do this 1,000 times, what's happening is variables are going to get a chance to weigh in and say, hey, I'm important in explaining banding. And I can look at all 1,000 trees and summarize that. So I'm going to close this right here, and then I'm just going to open up this output called column contribution. And so across the 1,000 trees, there's going to be variables that are going to come into the tree more often than others. In fact, the one that came in the most is viscosity. One that came in the second is this roller durometer. The one that came in third is paper mill location, and fourth is anode space and wax and so on. And then I've got some that just barely ever made it in. So even when the important variables weren't a part of being considered, these variables just very rarely came in. And so now I was able to automatically, very rapidly build 1,000 different trees, subsetting which variables were part of the consideration set, looking across those 1,000 trees and taking a look at which variables got put in more than others. And so now I'm able to see that, hey, maybe, for example, I'm just going to pick the top 5 just to illustrate. I may identify that, you know what, these 5 seem to be the ones that are worth thinking about. And maybe now I'm going to run an experiment, for example, where I'm going to select, in this case, paper from the different mills and then move these variables. And maybe some of these other ones aren't hard to change as well. And so I might expand the experiment. But I was able to take this problem that has more variables, 26, than there are observations, 17, when it's very difficult to build a model like that, and then let JMP automate this process of building 1,000 of them, giving each variable a chance to vote and saying, hey, I'm important or not in this, predicting or explaining banding. Because again, trying to build just one is very difficult with so few data, because it just doesn't allow many variables to even weigh in as being important if they are or not. And so this is this technique. It's called Bootstrap Forest. So think of the idea as, instead of building one tree, it's building a forest, well, in this case, 1,000 trees. And the bootstrapping is coming from this idea that it's actually doing it 2 directions, selecting the variables and also randomly selecting the observations. But I think for now, I'm just sort of illustrating the idea of the variables being selected, and that's the bootstrap part. Really, really cool way to find a set of variables that might be the most predictive or explanatory of a response when you've got one of these scenarios like this. Massive number of variables, but a few observations. And again, I know those are things that we might not traditionally teach in a classic statistics class, but this is the reality. When you get out there, we have so much data that's being measured now, so many variables, that we're going to run into this scenario. Your students are going to run into this scenario where they have to sort of sift through a big problem like this to try to find out the key variables that might be driving an outcome. And so I think this is a really quick tool, really easy tool in JMP to do that. And you saw how easy it was to do. And again, you might be like, well, that's kind of complicated for students. Well, if you're teaching them partition trees, right? If you're teaching them the concept of building a tree, then I don't think it's that far of a leap to say, let's build 1,000 trees and look at the results across all 1,000 and let JMP summarize those results for us. I don't think that's too complicated, right? We're taking advantage of computing power. Okay, I'm going to close that up. And the last one I'm going to look at here is, this is going to be data from measurements from a spectrometer made on sort of these little chemical specimens. And if you're familiar with or not familiar with what a spectrometer does, it's measuring the intensity of something across different wavelengths. And so it turns out I've got basically 202 wavelengths. I can kind of scroll all the way over. And then the data is sort of this intensity measurement. Now, what is that? Well, it's probably easier if I just kind of show you what that looks like here. Well, let me explain a little bit more, sorry. So there are 10 specimens that were made in a lab. You see that S1 through S10 lab. And then I've got 10 specimens that were measured when it was produced in the manufacturing environment, okay? So I'm going to show you what does that look like. Okay. And I basically just used the graph builder, but I'm going here automatically because I changed the color and everything to make it easier to see. So that's what data from a spectrometer might look like. And so the red ones are those coming from the manufacturing environment, and the blue ones are coming from the lab. And let's say the question or the objective is, where is there more variation? Is there more variation in the lab specimens, or is there more variation in the manufacturing specimens? And when you're just looking at one variable, well, that's easy, right? You just make some histograms and box plots and maybe calculate the standard deviation, and it's very, very easy to compare it in one dimension. But that's not what we have here. We have a lot of dimensions because we've got all of these wavelength values, right? So the data is a lot more complicated, and it would be hard to say, where is there more variation? In fact, I'm going to just zoom in here so you can see what this looks like a little closer. I'm just going to zoom in. Okay, so remember, the red are the manufacturing specimens and the blue are the lab specimens. And imagine trying to get in there and eyeball this and saying, which one has more variation, right? It's a little challenging to see that. I'm going to scroll kind of around. You might look and like, well, maybe it looks like it's the blue ones, maybe it's the red ones. It's not easy to see. I mean, this is sort of a little bit more of a complicated problem than your standard. Let me zoom back out here so we can get back to that view. This is a little bit more complicated problem, but again, we're moving into the age of big data, a lot of data, many variables, more complicated problems than just a single variable measured, and we can just look at histograms and box plots and summary statistics. So the problem is, how can we describe the variation in the blue measurements, the blue specimens, the lab, and then the variation in the manufacturing specimens, the red ones, and then somehow compare them? Okay, sounds like a very challenging problem. Well, there is a tool in JMP called Principal Components, and let me just open up a screen here just for those who don't know what a principal component is. Basically, what a principal component is it's going to create a linear combination. It's going to create a linear combination for each of those specimens going across all of those variables. And it puts these little weights on, that's the A11 and A12, et cetera. Actually, it standardizes the data. So instead of looking at the actual measurements made, it's sort of standardizing it. So that's why I turned it into Z's. But basically, it's going to create this linear combination. So it's going to turn all of those variables into just one, called principal component 1, and then the second one's principal component 2. And if you're not familiar with this, the idea is that it turns out that the principal component 1, that new variable, which is a reduction of all of those variables into just one, that variable will have the largest variation. And then principal component 2 has the second largest variation, and so on. And all these principal components are independent of each other. So it's creating these new variables that are independent. Okay. So to run a principal component analysis, it's not too difficult. We just launched the principal component analysis platform. We put all of the variables in here, and then we run. Okay. Now, what did it just do? Well, now I'm actually I saved some stuff here, so I'm just going to show you. This will, I think, will be much easier. So I created 2 new variables, principal component 1 and principal component 2. And you see I've got 10 measurements for the lab, 10 measurements for the manufacturing environment. And what are those? Well, basically, if I find weights, so I put a weight in front of that one, 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 and so on, and add all that up, I've created a linear combination, and I've basically turned it into a number. And I can do that for all 20 specimens, 10 lab, 10 manufacturing. That's the first principal component. And I also saved the second principal component, which is another linear combination, which is independent of the first. So these 2 variables have a correlation of 0. This principal component 2 will have the second amount of variation. So think of it as I'm reducing the data, all of those variables, to just 2 variables. And those 2 variables are squeezing out as much information out of all of those variables as possible. Okay. So I've got 200 different variables here, right? Scrolling across, there's 200 different variables, and I've reduced 200 down to 2. In other words, I've taken these 200 variables going across the x-axis and turned it into 2. And that sounds crazy. Well, let me show you a graph of those two principal components against each other. So this is just a scatter plot where principal component 1 is on the y-axis, principal component 2 is on the x-axis. And don't worry about what the values mean. In fact, in this case, they don't have any meaning. Just remember, they're a way of reducing these 200 variables down to 2. That's try to squeeze out as much information. And they turn out to have a mean of 0. That's why I centered it at 0 and drew those lines. So remember what we've got here. All the lab specimens are shown in blue, and all the manufacturing specimens are shown in red. Now, remember when I showed you this first graph and said, well, can you describe the variation here? Well, it's too complicated. It's really hard to see what that variation is. But now that I've reduced it down to this graph, if I ask you, where is there more variation in the manufacturing specimens or the lab specimens? Well, it's very, very easy to see it's the manufacturing specimens that have more variation. Look at this one out here, this one out here. So if you look at the cloud of red points and compare it to the cloud of blue points, you see how these blue points are very close and the red points are more spread out? That's basically a way of examining this graph and saying that there's more variation in those red lines than there are in the blue lines. And that's very hard to see there. Perhaps impossible to determine there. But it's very easy to see the variation is larger in the manufacturing. In fact, another thing that's interesting is if I look at the ones that are the furthest out, that's observation 17, that's observation 19, that's observation 20. So towards the end is when the variation gets the largest. So if these things were measured in that order, that could be giving us some more information there too, that as we go across, oops, let me get back to this one. Yeah, that as these were being measured, the variation starts getting larger as I start moving towards the end. Again, if that's how these were collected and done in, say, the order of which they were manufactured. Okay, so what JMP very easily did is it took this problem, a highly, highly dimensional problem, okay, a lot more variables than there are observations, and said, can I reduce this in some way and turn it into a smaller number of variables, in this case 2, and in doing so, can I look at 2 dimensions, like I can here, and see how the variation compares? And it's very easy to see how the variation compares. So again, a highly dimensional problem reduced down to a much smaller dimensional problem, and I can just quickly visualize that variation. Okay, so I showed a couple things in these data sets here. One was just graphically, and that was the insect problem, where it was very hard to look at so many time series graphs. So instead, let me just open this. Oops. So remember, with the insect problem, it was so much easier. Well, if I just, instead of looking at all the time series graphs, why don't I just do a visual and sort of animate that change, and I can easily see when the populations are more dramatically increasing than when they're not. I can also see when sites get measured, okay, which was really, really hard to see in the time series. I did this idea of, let me compare doing a one-way ANOVA 125 different responses, so I can run 125 different one-way ANOVAs, and I did that, and I was able to sort of run these 125 ANOVAs and look at graphs that summarize the results of 125 ANOVAs for me, identifying the ones that are significant and not significant, and it makes those adjustments for the fact that I've got 125 comparisons going on. I had the printing example that has more variables than observations, and it's hard to build a partition tree like that to give every variable a chance to weigh in on its importance. So I built 1,000 trees automatically, selecting variables for each tree to give each variable a chance to weigh in, and I was able to look, run that, oops, and ranked the ones that were most important to least important by giving it a shot to be involved. And then the last one was looking at this highly dimensional spectrometer problem, trying to describe the variation in that graph, that view, in that many dimensions, and instead turned it into 2, and it was very easy to see. So I think I gave a set of sort of not typical, traditional, easy to solve problems, and within an hour, I analyzed all 4 of those really quickly and showed you the tools in JMP to make that super easy to do. All right, thanks everybody. Take care. Please be safe and healthy.